Quantum mechanical model of an atom is the model from which we can find the most probable address for an electron in an atom. As we know, the wave character of an electron and uncertainty in its position and momentum gave a serious blow to Bohr's model of an atom. According to Bohr, the electrons revolve around the nucleus in certain well-defined circular orbits. But the idea of uncertainty in position and velocity overruled the Bohr's picture of fixed orbits. Thus, the classical mechanics could not describe the behavior of electrons in atoms correctly. Therefore, the scientists started looking for a model which could incorporate the dual character of atom. The, this resulted in a new approach called quantum mechanics or wave mechanics. Quantum mechanics was developed independently by Werner Heisenberg and Erwin Schrödinger. Now, on the basis of quantum mechanics, Schrödinger proposed a model of an atom which considered wave-particle duality of matter. This particular model was known as quantum mechanical model of an atom. In 1927, Erwin Schrödinger described the wave motion of an electron in some three-dimensional space by a lengthy mathematical equation known as the Schrödinger wave equation. Now you can all see that this particular equation is so complex. This is this is the Schrödinger wave equation proposed by him. Now this particular model also explained the electrons being a particle exhibits the wave nature. That means it has both particle and wave nature. Now we should come to the concept of quantum numbers. Quantum numbers are actually a set of four numbers. The most accurate and most probable address of the electron can be found out using these four quantum numbers. Now, as we know that orbitals represent regions in space around the nucleus where the probability of finding an electron is maximum. A large number of electrons orbitals are possible in atom. There are infinite orbitals. These can be distinguished by their size, shapes, and orientation. Now, to describe each electron in atom in different orbitals, we need a set of four numbers known as quantum numbers. These are designated as N, L, M, and S. These four numbers are called quantum numbers. Now, the first quantum number is the principal quantum number. The principal quantum number represents the main shell of the atom. It's represented by the symbol small n. For example, n is equal to 1, 2, 3, 4. They are the orbits and have names like K, L, M, N. They are actually the symbols. Now, the principal quantum number gives the average distance of the electron from the atom and so the energy. Now, when we go from one main shell to second to third to fourth, the average distance of the electron increases from the nucleus, and so the energy of the electron also increases. The principal quantum number is the main shell of the atom. The second quantum number is the azimuthal or angular momentum quantum number. It actually determines the angular momentum of the electron. Angular momentum we all know is mvr, is the momentum in the circular orbits. It shows the subshell where the electron resides. It's actually a type of hierarchy like shell, subshells, and the orbitals. It's represented by a symbol L. The formula for finding the total number of subshells in a shell is 0 to n minus 1. It's actually the range from which we can find out 0 to n minus 1. For example, if n is equal to 3, then the number of subshells are 0, 1, 2. Alright. Now the number of azimuthal quantum number are equal to the principal quantum number. Now take the previous example, n is equal to 3 and the subshells are 0, 1, 2. That means it's the same 3, 3. Alright. Now here it is a table given. Now each subshell has its name and has got its shape. For example, if it's a zero subshell, the name of the shell is S and the shape is spherical. For first subshell, the name is P and the shape is tumble shaped. For the second, it's D and it's complex double tumble. And for three, it's F and more complex multiple lobes. Now, these letters SPDF originate from terms sharp, principal, diffuse, fundamental. They are really important. Now, here it is the angular momentum quantum number symbol. Here it is a table showing everything about the angular quantum number. Now, it is given that principal quantum number n 1, 2, 3, 4. Then how many angular momentum quantum numbers are there? And then there's subshells. Now, the first principal quantum number, the number of subshells are 0. So, for 0, it's S, one subshell. For the second, there are 2. L is equal to 0 and L equal to 1. So, for 0, it's S. For 1, it is P. So, there are 2 subshells. And for third, it's there are 3 angular momenta. L equal to 0, L equal to 1, and L equal to 2. SPD. You can correlate with that. 3 subshells. 4 L equal to 0, 1, 2, 3, SPDF. You can all find out that the principal quantum number, the total number of principal quantum number is equal to the angular momentum quantum number. So each subshell has got its own shape and own name like 0 S, 1 P, 2 D, 3 F. So now the third quantum number is the magnetic quantum number. It actually represents the orbital of an electron. So now it's the shell, the subshell, and now the orbital. They are represented by the letter m. The number of m can be found out by the formula minus L, 0, and plus L. For example, the value of L is 1, so the value of m will be minus 1, 0, and 1. The total values of m can be found out by the formula 2L plus 1. For example, the L value is 3, then the total number of orbitals will be 7. Another example, if the value of L is 2, the total number of orbitals will be 5. So, now hope it's clear. Now we have a chart here which provides us everything from the principal quantum number to the orbitals. We have the principal quantum number here 1, 2, 3, and 4. And here aside, we have the subshells L. For the subshell 1, we have 0. For principal quantum number 2, we have 0 and 1 subshells. For 3, 0, 1, 2. For 4, 0, 1, 2, 3. Now, for the subshells, the types of orbitals, we can do one thing. This 1s, 1 is the principal quantum number, and s is 0. S comes from 0. From the previous, we had studied about this. In the 2, 2 is the principal quantum number, and s comes from 0. 2 is the principal quantum number, and p comes from 1. Then 3 is the quantum number, then s comes from 0, p comes from 1, p comes from 2, and so on. Now in this particular column, we have the magnetic quantum number or m value. For L value of 0, there is only one value of m, which is 0. In the second principal quantum number, for the value of 0 in L, we have one value of m, which is 0. For 1, we have three value, minus 1, 0, and plus 1. We had seen in the example. For 0, we have 0, 1, we have minus 1, 0, plus 1. So you can see that by the formula of 2 plus L, we can easily distinguish that 1L has 1, and 2L has 5, and 3L has 7. And in this, we can find out this by the formula of n square. They are the number of orbitals in the shell. Third quantum number is the magnetic quantum number. It actually represents the orbital of an electron. So its shell, subshell, and then orbital. They are represented by the symbol m. The number of m can be found out by the formula minus L, then 0, and then plus L. For example, the L value is 1, so the value of m will be minus 1, 0, and 1 by the formula minus L, 0, and plus L. The total values of m can be found out by 2L plus 1. For example, the value of L is 3, so the total number of orbitals will be 7. Another example, if the value of L is 2, by putting the formula 2L plus 1, the total number of orbitals will be 5. So hope it's clear. So here now we have a chart which gives you everything from the principal quantum number to the orbitals in the shell. We have the principal quantum number 1, 2, 3, and 4. We have the subshells 0 for 1, 0, 1 for 2, 0, 1, 2, 3, and 0, 1, 2, 3 for 4. We have done this previously. Now the subshells, the types of orbitals, it is 1s, 1 for the principal quantum number, and s by 0. By the principal quantum number, 2, s for 0, then 2 for the principal quantum number, and p for 1. 3 by the principal quantum number, and s by 0, p for 1, and d for 2. We have done this previously also, and so on. Now in this particular m value column, the number of m value is 0 for L is 0. For the principal quantum number 2, we have 0 L value, and then the value of m will be 0. For 1 value of L, there will be 3 magnetic quantum numbers, minus 1, 0, and plus 1. For 0, it's 0, 1, minus 1, 0, plus 1, 2, minus 2, minus 1, 0, plus 1, plus 2, and so on. We can get this by this formula 2L plus 1, that how many number of magnetic quantum numbers are there. The next column tells us about the number of orbitals in the subshell. So you can count this 1, 1, 3. All this we can get from this particular formula. The last column tells us about the orbitals in shell. So these can be found out by n square. See, n is the principal quantum number. So squaring 1, we get 1. Squaring 2, we get 4. Squaring 3, we get 9. And squaring 4, we get 16. So hope it's clear. The last quantum number is the spin quantum number. It's observed that the electron in an atom is not only revolving around the nucleus, but is also spinning around its own axis. This quantum number describes the spin orientation of the electron. It's designated by ms. Since the electron can spin in only two ways, clockwise or anticlockwise, therefore the spin quantum number can take only two values, half and minus half. This quantum number has a value independent of the values of the other three quantum numbers. Instead of giving numbers for ms, plus half or minus half, the two orientations are usually designated by arrows, which is upspin and downspin. Here you can see this is the up one and this is the down one. Pauli's exclusion principle. After setting the rules for the possible values of quantum numbers, we can calculate the maximum number of electrons that can be added in each shell and subshell in an atom. For this, there is a guiding principle known as the Pauli's exclusion principle. It states that no two electrons in an atom can have the same values for all the four quantum numbers. This principle can be easily understood. We have learned that an orbital is specified by three quantum numbers, n, l, and m. Since an electron in an orbital must have the same values of n, l, and m, it follows that it can have two values of s as either plus half or minus half. In other words, an orbital can have at the most two electrons provided their spin quantum number are different. For example, consider the case shell, where n is equal to 1, L is equal to 0, and M is equal to 0. So there are two spins, plus half and minus half. This leads to the conclusion that an orbital can have maximum 2 electrons. Moreover, if an orbital has 2 electrons, these must be of opposite spins. Thus, Pauli's exclusion principle also states that an orbital can contain maximum of 2 electrons.